Hi everyone. Today I'm going to talk about time lag multidimensional pattern connectivity, which is a novel functional connectivity metric for EEG and MEG applications. To start with, I'm going to define what I mean by multidimensional data. So in every brain region like this, there are multiple vertices or voxels, each having a specific time series. But what univariate and conventional methods usually do is reducing all of these vertices just to one vertex by using PCA, averaging, and other stuff. The problem is that this reduction usually leads to loss of information and false findings, and that is something that we are not interested in. So that's why multidimensional approaches have been of a great interest in recent years. The main motivation behind our new method were two groups of studies which aim to look at brain connectivities between pairs of regions in terms of their multidimensional patterns of responses. The first study actually transformed their multidimensional space into another space by actually using PCA. And then they took the first 1, 2, 3 principal components to characterize their final multidimensional space. Actually, with doing so, the real and genuine voxel-to-voxel relationship is being lost, and that is a limitation that has been covered in the next study. So what they are trying to do is to find out if pattern like this one in one ROI can predict another pattern in another ROI through a linear transformation like this one. The other point that I should highlight here is that most of multidimensional connectivity methods have been proposed for fMRI, which despite its very well spatial resolution, is really limited in order to track changes in millisecond scales. And that's why we are introducing time lag multidimensional pattern connectivity, which is well suited for EEG and MEG applications. And because it's EEG and MEG, we need to deal with leakage. And to do so, we subsampled vertices using clustering. Okay. So essentially, we want to see how well patterns of ROI X, so these are patterns of ROI X at different time points, and these are patterns of ROI Y at different time points. So we want to find out how well patterns of ROI X at time point Tx, like this one, can predict patterns of ROI Y at time point Ty, like this one, through a linear transformation. To do so, we use tenfold cross-validated ridge regression, and we use explained variance as our connectivity metric. In this case, the best score would be 1, suggesting that there is a strong linear connection between two patterns. And if we get something like 0 or even negative values, it suggests that there is no relationship or there is no linear relationship between two patterns. Okay, we ran some simulations to compare and evaluate the univariate and multidimensional approaches. We considered 3 possible scenarios. For example, we considered 2 patterns which are completely independent, like having 2 random noises. So there is no mapping between these 2. On the other hand, we have 2 patterns which are completely and strongly connected with each other through a linear transformation or mapping like this. And the point here is that all vertices in every pattern are independent from each other. So that's why I've called this one multidimensional effect. In the middle, we have another relationship, another scenario, which there is a relationship between 2 patterns, but in every pattern, vertices are somehow are showing the same amount of brain activity, and they only differ in their actually the amount of noise. So basically, they are showing the same thing, and that's why I've called this one univariate effect. We computed the connectivity for both univariate and multivariate approaches for different scenarios, and we also varied critical parameters such as different levels of SNRs, number of trials, and number of vertices. Well, this is the result of the first scenario in which we had 2 independent patterns. So on the top, we have the result of univariate approach, and here we have the result of multidimensional approach. On x-axis, we have different number of trials, and y-axis shows the connectivity score, which is explained variance. So in every figure, we have 4 curves representing different number of vertices in ROI X and ROI Y. So both approaches, for both approaches, we see that the connectivity is always negative or close to 0, suggesting that when there is two random things, when there are actually two unrelated patterns, both methods are doing good and they are immune against false positive errors. Well, this is the result for the second scenario in which we had two univariate effects. On x-axis, we have different levels of SNRs, and y-axis shows the connectivity. We have three different curves for univariate approach and three curves, green curves for multidimensional approach. In the middle SNRs, we see that univariate approach is slightly doing better than the multi-dimensional one. However, this method is still sensitive to some amount of data variance. Here we see the result of the last scenario in which we had two multidimensional effects. We see that this univariate approach fails to capture information, fails to capture connectivity, and it cannot explain more than 20% of data variance. Whereas multidimensional approach gradually increase and reaches 1 in really ideal cases. Well, we also apply this method on a real data set to compare the connectivity of semantic networks in two visual word recognition tasks, namely lexical decision task, which has less semantic processing, and semantic decision task, which has more semantic processing. So essentially, it's a comparison between more semantic and less semantic tasks. We consider 6 ROIs, including left and right anterior temporal lobes, as two critical regions for semantic representation. Inferior frontal gyrus and posterior temporal cortex as two important regions for semantic control. Visual area is the input of this network, and also we considered angular gyrus because there are a lot of arguments about the role of this region in the semantic network. Well, just to give you an idea how this connectivity looks like, let's take a look at this example, which is the comparison between the connectivity between right ATL and posterior temporal cortex at different latencies. So the color bar is showing explained variance as the connectivity metric, and here on X and Y axis we have time latencies. So the first column is the connectivity for more semantic tasks. The second one shows the connectivity for less semantic tasks. And here we have their comparison, and these yellow bright colors show the latency that have been modulated by task demands. I've put all these p-test results for both univariate approach and multidimensional approach for every pairs of regions in a bigger matrix like this one. So upper diagonal shows the connectivity for univariate approach, and lower diagonal shows the result for multidimensional approach. What is interesting here is that we are getting more connectivity modulation with multidimensional approach compared to univariate one. And this is not just a random thing, but it seems to be really meaningful, and it nicely fit with the literature of semantic, as we have a connection between left and right ATL, IFG, and posterior temporal cortex. So all these four semantic regions are connected to each other. And if we look at the connectivity between angular gyrus and other semantic regions, it's really so sparse. Okay, this figures summarize and shows the performance of different methods on the same data set in two time windows, so early time points and late time points. In our previous study with coherence, we've only got modulation of connectivity between left and right ATL in early time points, and then between left ATL and IFG at later time points. Whereas with this new multidimensional connectivity, we are getting all these actually 6 connections. So we see that 4 classical semantic regions are being connected to each other at both time windows, of course, with different strength. And there seems to be 2 potential networks, one in the more frontal and temporal regions of the brain, including these 4 regions, and one in the more posterior regions of the brain, including visual area, angular gyrus, and posterior temporal cortex. Well, to summarize and conclude, multidimensional pattern connectivity is a new functional connectivity metric. Our simulations showed that this method is immune against false positive errors and performs really good in both univariate effects and multidimensional effects. Regarding our specific semantic question, we got more and richer connectivity with multidimensional approach compared to univariate approach. And there seem to be two meaningful networks, one including left and right ATLs, posterior temporal cortex and IFG, and one including visual area and large iris and probably posterior temporal cortex. And in general, we got more consistent connectivity between left ATL and other semantic regions compared to angular gyrus and semantic regions. As to the future steps, we are going to actually apply a nonlinear function like neural networks and introduce a nonlinear version of multidimensional pattern connectivity. And probably the next step could be presenting its grandeur style type. That's it for me. Thank you for your attention.